Okay, welcome everybody to our second to last installment of the Great Lectures.
Welcome everybody.
Sorry, I was getting
Installment of the Great Lectures. Welcome everybody.
Let me just pause that for a second. Don't know where I'm getting the feedback from. Okay, let's try that again. Hopefully not getting feedback now. So welcome everyone to the second to last installment of the Great Lakes Lecture Series for this summer. We've had a great list and roster of speakers so far, and today is no different. So I'm very glad to introduce to you Dr. Andrew Fullard, who is going to talk to us today about science and the Star Wars and how that relates to science. He's been a fan of Star Wars for most of his life, as I'm sure many of you watching today have as well. And by his own admission, he says he knows way too much about a galaxy far, far away. So that will be of great interest to hear about today. He obtained his PhD from the University of Denver, and recently actually has moved here to MSU to work with Professor Kersendorf to study the explosions of dying stars. So I'm sure if you have any questions about that, he will also be able to answer you there. So without further ado, let me hand you over to Dr. Fullard, and thank you very much for joining us today.
Yeah, thank you for the introduction, Dan. I'll start sharing my screen. There we go. Okay, so the science of Star Wars. As Dan mentioned, Star Wars is near and dear to my heart. I've definitely watched all the movies since I was very young. Know much too much about all the greater expanded universe of Star Wars, but I'm going to keep things a little more real, I suppose, today in this short talk. I'm going to go through some of the real examples of things that exist in Star Wars, and maybe some ways that things in Star Wars could be implemented in the real world. I really do strongly encourage you to ask questions about any of this, any burning questions you have about science in Star Wars, any questions you have, as Dan said, about my research area here at MSU, which is supernovae, exploding stars. And I'm also happy to talk about other stellar physics and astronomy topics as well. So we're going to begin our journey on the desert planet Tatooine, Luke Skywalker's home planet, probably the most famous planet in the Star Wars saga. It's scorched by the twin suns that it orbits, so dry, desert, hot. And here we have a wonderful rendition of the twin sunset that's seen in a lot of the movies. Now, are there planets like Tatooine in our galaxy? And the answer is yes, there are. There are quite a number of planets that orbit twin suns. In fact, one of the most recent discoveries has been TOI 1338b, which is an exoplanet, that is a planet outside of our own solar system, that was discovered by the Transiting Exoplanet Survey Satellite, or TESS. So you can see here in this schematic that you have two stars at the center of the system orbiting each other, and then you have this TOI 1338b, the small planet, orbiting around these two stars. So on this planet, you would indeed start to see a binary sunset. As this planet rotates, one star would set and then the other star would set. In the case of this particular system, it's over 1,300 light years away. So a light year is a measure of distance in astronomy. It's the distance that light can travel in 1 year. And it's in the direction of the constellation Pictor. So if you know your constellations, you can look that up and look in that direction. I think Pictor might be in the southern hemisphere, so it might be a little difficult for Lansing. But if you're ever in the south of the Earth, you may be able to look towards where this planet is located. You can see the stars are quite different here in this artist's impression. One of them is the larger star is about 10% more massive than our sun, while the smaller star here is much cooler and dimmer and only 1/3 of our sun's mass. 1338b is the only planet we know about in the system. So it's orbiting circumbinary, that is, it orbits around both of the stars in the center. You can see here we have capital A and capital B for the stars, because astronomers love to confuse each other and the general public with their names for everything. And then here we're seeing an example of a planetary transit. This is how the planet was detected. I'll talk a little bit more about other exoplanet detection methods, but here you can see, as time fast forwards, as these stars orbit each other, the brightness dips. And that's because the dim star, when you're looking at them both at the same time, you get the sum of the brightness that we see with our telescope. And then when one of the stars is in front of the other, you see a dip. When there's a small dip, it generally will mean the dimmer star has been eclipsed. And when you have a bright dip, when you have a large dip, I should say, that means the dim star has gone in front of the bright star. Now, the very interesting thing about this particular planet and circumbinary planets in general is they're very difficult to pick out of data. This planet was actually discovered by a high school student during an internship, because we actually need people to go through the data and look at it. Usually we use computers to automatically discover these things. But in this case, for these complicated systems, you really need people to go through and look at the data. And so this high school student discovered eclipses, here marked in green, that were caused by the planet itself and not by the two stars orbiting each other. The planet, by the way, is it's not an Earth-like planet, unfortunately. It's 7 times larger than Earth. It's quite difficult for us to discover Earth-like planets because they're so small. And the planet and the two stars orbit all in about the same plane. So as you saw in the image there, everything is quite edge on, which means they eclipse very clearly. So yes, this planet was discovered quite recently. There are a number of other circumbinary planets that have been discovered as well, but I think this one is quite exciting, as they're discovered by a high school student. You can see here an example of what's called precession. So the orbit is changing very slowly with time as we observe it from Earth. And that means after a certain amount, I believe after a few tens of years, the eclipses are going to stop happening. So we need to get as much information about systems like this as fast as possible. Otherwise, we're going to lose the ability to understand them. And then here at the end of this video, this is a nice rendering of the TESS mission. So this is the satellite which is currently orbiting and getting huge amounts of exciting data on stars, supernovae, and of course exoplanets. Now this leads me into, how do we discover exoplanets? Well, I talked about transiting eclipses. That's also known as transiting photometry. Photometry, just a word that means the measurement of light. And what's exciting about transit photometry is that using telescopes like TESS, we can actually look at the depth and the amount of time that it takes for the transit to occur. And that can tell us a huge amount about things like the size of the planet, the length of the orbit. And if we know the length of the orbit and the mass of the star, we can actually determine the mass of the planet as well, which tells us huge amounts about its, potentially about its composition, about whether it could be Earth-like or not. One of the other common methods for discovering exoplanets is through radial velocity. In this case, the gravity of the planet pulls slightly on its parent star, just like the Earth does on the sun, and the sun does on the Earth. This creates a wobble in the star. This wobble can be detected by looking at the light coming from the star, because when the star wobbles towards the Earth, the wavelengths of light get compressed. That causes a blue shift. And when the star wobbles away from the Earth, the wavelengths expand and we get a red shift. And this red shift and blue shift information can tell us about the masses of the planets in the system, and we can disentangle multiple planets in this way. And one of the easiest methods, you might think, is direct imaging, where we simply point a powerful telescope at a star and take a picture and say, are there planets there that we can see? Of course, this method is very difficult in reality because you need a very large telescope to disentangle the signals from the planet and the star. Stars are so much brighter than planets. All you're seeing from planets is reflected starlight. And the stars are so much brighter, they will drown out the signal from the planets. That means you need extremely powerful telescopes or very clever techniques to get planets with direct imaging. It's also difficult to observe planets through direct imaging if the system is more edge-on, like in the case of TOI 1338. So direct imaging is great for relatively nearby systems where the orbit is almost face-on, so that we can look down the pole of the orbit, as it were. One of the more interesting methods that isn't used a huge amount, but is still quite exciting, is so-called gravitational microlensing. And this is uses a property of general relativity, where masses, general relativity, which of course is our best theory of gravity, where masses bend space-time. Space-time being what? The 3 dimensions of space and the 1 dimension of time that make up our universe. And so if you have a target star where you want to see if there's a planet around it, and it passes in front of a background star, the foreground star, the target will act like a lens. It will bend light around it, magnifying the background star. Now, using certain modeling techniques, we have a good idea of what the mass of most stars should be if we can observe their spectra, which is another way of observing them to discover the elements in their atmosphere. And if we know the mass of the lens star, we know how much lensing should occur. And if more lensing occurs than expected, then there's a planet there, possibly. The downsides of this method are that it's quite imprecise. You can only really measure the mass of planets and not much else about them. It's very difficult to reproduce, unfortunately. It requires your target star to pass in front of background stars. And the stars that the planets it usually detects are generally very far away, many thousands of light years, which means that it's very hard for other telescopes to follow up and investigate the system. So I'm just going to, so I'll talk about Cloud City. So moving on to another location, Star Wars, Cloud City, the home of Lando Calrissian, or at least one of his homes, the one that he's administrating in The Empire Strikes Back. Could Cloud City exist in reality? Well, one thing you would need first is, if it's in the atmosphere of a gas giant, you would need some kind of habitable layer in that gas giant, where the temperature is of the kind of temperature that we have today on Earth, somewhere between 0 and 100 Fahrenheit. And then you would also want some kind of breathable atmosphere, mostly consisting of about 25% oxygen and then other inert gases that may be nitrogen like Earth, but maybe other gases. The other thing you would need is a lot of anti-gravity technology, because otherwise the immense gravitational pull of gas giants, being very massive planets, would cause everybody on the Cloud City to be very, very short and rather squashed. So you need some powerful anti-gravity technology for this to work. But it's actually been suggested that this kind of Cloud City could be possible in the atmosphere of Venus. There's actually a region of Venus's atmosphere which is a relatively reasonable temperature. You may know Venus as the planet with extremely thick atmosphere, very high pressure on its surface, and with lots of acid rain. But there are areas above the acid rain clouds where it may be possible to site some kind of habitat that's similar to Cloud City, where people can live and work. This is obviously a very long way off, but it's an exciting prospect. And recently, there's been a lot of hullabaloo in the scientific community about the possible detection of phosphine in Venus's atmosphere. I'm not going to talk too much about that because it's quite it's quite a touchy subject for the scientists who worked on it, and I personally don't know a huge amount about the science behind it, but there's been a lot of published articles back and forth about this subject, and I recommend you look up Venus phosphine if you want to learn more. Phosphine, by the way, is a gas that is thought to be produced only by living things. Any amount of phosphine, the amount of phosphine that is supposedly detected in Venus's atmosphere, could not have been produced simply by its volcanic activity or other non-biological means. So that's very exciting potential life on Venus. I recommend looking up and deciding for yourself which side you agree on in that. Now, as I mentioned, Cloud City is in the atmosphere of a gas giant. A couple of other gas giants in Star Wars are Endor and Yavin. But we don't usually see the gas giants in Star Wars. In fact, what we see are their moons. Endor in Return of the Jedi, of course, the forest moon of Endor is where the Ewoks live. And on Yavin in A New Hope, that's where the Rebel base is, also shows up in Rogue One. Now, both of these moons in Star Wars seem to be habitable. They have atmospheres, weather, flora and fauna. You know, the Ewoks live on the forest moon of Endor. So the question then might be, can such moons exist in our galaxy or in our universe? And again, the answer is possibly. I should first mention, of course, I'm using the term exomoon here, which very much like exoplanet is simply moons that orbit planets outside of our own solar system. Where, of course, the definition of planet itself is a bit complicated. I'm sure everyone remembers when Pluto was no longer made a planet and became a dwarf planet. And technically, a moon can also orbit a dwarf planet. But generally, it will be a body orbiting a non-stellar object in a system that has enough mass to keep itself together. So probably the closest thing to these in our own solar system, or one of the closest things, aside from the moon of Saturn, Titan, are the Galilean moons of Jupiter. You can see here on the left all the moons presented to scale. From top to bottom, we have Io, a volcanically active moon. The bright colors are caused by all of the sulfur and other volcanic gases and minerals that are deposited on its surface. Now, Io is very small. It shouldn't be volcanically active for its size, but the immense gravitational pull of Jupiter creates strong tides on the inside of Io, much like the moon creates tides on Earth. And these tides heat up the inside of Io through friction, liquefying it. And this means you have volcanic activity on what would otherwise be a very inert body. Below that, we have the icy moon of Europa. Europa is also tidally affected by Jupiter. And what's exciting about Europa is it has a very thick layer of ice on the surface. And many scientists think that below that ice, because of the heating from tidal friction, there may in fact be an ocean of water, of liquid water below the ice. And because of the importance of Europa, there's actually going to be a new NASA mission going to Europa called Europa Clipper, which is scheduled to be launched in 2024. So I urge you to look out for that. It's going to be very exciting when that reaches Europa and unlocks some of the secrets of this moon. The other two moons of Jupiter aren't quite as, Galilean moons of Jupiter that is, aren't quite as exciting. We have Ganymede, which one of the largest moons in the solar system, is larger than Mercury, and Callisto, which is mostly made of ice and rock. And you might ask, well, why are these called the Galilean moons? That's because they were the moons discovered by Galileo using the first telescope in the 1600s. And in fact, these moons are very easy to pick out with binoculars or your own small telescope when Jupiter is up in the night sky. I strongly recommend you go look for them. It's very exciting to be able to see Jupiter with its own little moons orbiting it. It's like looking into another solar system. Of course, Jupiter has hundreds of other moons of various sizes, and we discover more all the time, which is very interesting. In terms of real exomoons, they're very difficult to detect. I already showed you the transit method for detecting exoplanets, and that's probably the only way we'll be able to detect exomoons anytime soon, because their gravitational pull is going to be much too small for any kind of radial velocity or gravitational lensing measurement, and they are going to be much too close to their planets for us to be able to have a chance of imaging them, as well as being incredibly dim. So using transit photometry, there has been one suggested exomoon discovery using the Kepler satellite, which is a mission very much like TESS, but Kepler is now defunct. But Kepler 1625b1 is the possible moon of Kepler 1625b. Kepler 1625b itself is a gas giant. In general, it's much easier for us to discover gas giants because they're very large. So they have very strong impacts on the light from their target, from their parent star. So we tend to discover gas giants. And the moon around this gas giant is currently quite under debate. We're not entirely sure if it's there. The signal is very faint, and it's going to need a lot more follow-up observations. There have been some done with the Hubble Space Telescope, which I'm sure you've all heard of, but they haven't been conclusive yet. So hopefully there'll be more observations of this system, and we can get a conclusive hint as to whether we may have another exomoon on our hands, or the first exomoon on our hands, I should say. What's particularly interesting about this exomoon, in the sense of Yavin and the forest moon of Endor, is that the host planet in this system is approximately in the habitable zone of its star. It has a surface temperature estimated to be around 20 centigrade, or minus 20 centigrade, or minus 4 Fahrenheit. Now, what's the habitable zone? Simply, that's an area around a star where liquid water could exist. Of course, that doesn't mean there can be life. That doesn't necessarily mean any of the other conditions for life will be met, but it's a tantalizing glimpse at the possibility of moons such as Yavin and the forest moon of Endor and so forth existing in reality. And there's no reason not to think that there would be more moons like this, given the huge number of moons around the gas giants in our solar system. Now, this is no moon, but the Death Star is a very powerful weapon in Star Wars. We see it destroying Alderaan in A New Hope. We see, of course, Starkiller Base destroying planets in The Force Awakens with similar principles. You might think, how much power is needed to destroy a planet? Well, based on calculations that can be done, based on the speed at which the material of the planet Alderaan explodes away from the superlaser, you can actually measure the power output of the Death Star, assuming certain things about Alderaan's composition as a rocky planet similar to Earth. And this means that the Death Star has to have a power output of approximately 5 times the continuous power output of our sun. Now, for a 900-kilometer diameter battle station, that means the energy density has to be immense, much higher, much more efficient than anything we can possibly comprehend. The most energy efficient thing we know of is our sun, which produces energy through nuclear fusion. So nuclear fusion is a process whereby protons, which are positively charged elementary particles, which make up the nucleus or the central part of the hydrogen atom, these protons smack into each other inside the sun because it's so dense. One of them becomes a neutron, which is a neutrally charged elementary particle. And the transition from proton to neutron results in a slight loss of mass. And this slight change in mass translates to a gamma ray photon, a high energy photon escaping because of E equals mc squared. Mass and energy are interchangeable. So you essentially convert that mass instantly to energy. And this continues down this chain you can see on the right here called the proton-proton chain, where protons continually are added until you end up with a helium nucleus. And this energy in the form of photons then dissipates out through the layers of the sun and reaches Earth. But like I said, the Death Star has to have significantly higher energy density than that. Now, what is a moon and is kind of like the Death Star, but isn't, is the moon of Saturn, Mimas, sometimes pronounced Mimas. So Mimas was discovered by William Herschel in 1789, but the giant crater on its face, also named Herschel after him, wasn't discovered until 1980 by Voyager 1, famous space probe that went past Saturn as part of its survey of the planets. And that was actually discovered 3 years after A New Hope. So of course, everyone immediately said, well, it's the Death Star, obviously. It's got a giant crater on its side, looks like the Death Star. The Cassini mission, another mission to Saturn, took this image in 2010. And some of the other images that Cassini took show that this impact crater, which is what it is, of course, it's not actually a superlaser dish. The impact crater on Mimas was such a strong impact that the opposite side of Mimas has been disturbed and broken up by this huge impact. A completely different but equally interesting fact about Mimas is that its heat map, its temperature map, looks like Pac-Man. This temperature map was taken by the Cassini probe using infrared light, which allows us to detect heat. And you can see the bright orange layers there in the shape of Pac-Man and his little pellet that he's about to eat are actually hot areas of Mimas, and the blue areas are cold. And it's actually very puzzling. When this was discovered, scientists couldn't explain why Mimas would have such strong temperature gradients like this, why it would have such different temperatures on different sides. What's been suggested in the 10 years since this image was taken is that Mimas is passing through high energy electrons. Electrons are negatively charged elementary particles, so almost the opposite of protons, but much less massive. And they stream out from the sun, out towards other planets. And in Saturn's case, its magnetic field constrains the electrons. It pulls them down. They spiral along magnetic field lines because of their electric charge. They interact with the magnetic field, spiral along it. And so there's this cloud of high energy electrons pinging around in Saturn's magnetosphere, which is our name for the essentially like the atmosphere, the extreme edges of the magnetic field. And Mimas passes through that. And so what happens is these electrons heat up its surface. At least that's the theory. They heat up its surface and create this interesting pattern in the direction of Mimas's travel. The warmth in the crater, Herschel crater, is because essentially the crater itself traps a little bit of heat from the sun. And that's why it's slightly warmer than the rest of the cold area. But I thought that was a fun little aside, obviously not Star Wars directly, but another fun fact about this Death Star moon. Now, how do we travel to all these exciting exoplanets and exomoons to find out if they're habitable? Well, in Star Wars, of course, we use hyperspace. Your ship blasts off into hyperspace, the stars bend around you and you enter a blue tunnel, and then you come out the other end in a new location. How could faster than light travel along these lines actually occur in reality? Well, there's obviously been a lot of theories proposed about this because it's a very exciting subject, but here's a few that I think are some of the least ridiculous. Probably the one that's most similar to hyperspace in Star Wars is the idea of a wormhole. So a wormhole is a hole through space-time. If you imagine space-time as a flat sheet of paper, you fold the paper in half, then you punch a hole through it, then you open the paper up again. A wormhole is as if when you enter one of those holes, you can immediately exit the other one. Or perhaps you would take some travel time. It's very unclear. So that's how wormholes are. They're holes in space-time that connect disparate areas of space-time. It's very unlikely that we will be able to harness wormholes anytime soon, especially because a lot of the theories about them anyway require something called negative energy to keep them open and stable. Negative energy is a theoretical concept that we have no experimental evidence for yet. And personally, it's not something I take particularly seriously, but it's the way that if wormholes exist, it's one of the postulated ways to keep them open. Another use for negative energy is another possible faster than light travel method called the Alcubierre drive. This was actually proposed by a graduate student at the University of Boulder, Colorado, a few decades ago. And the idea of the Alcubierre drive is that you break the faster than light barrier, not by moving a ship fast, but by moving the space around it. So the ship has some kind of powerful negative energy drive which contracts the space-time in front of it and expands the space-time behind it, and it's space-time itself that moves faster than the speed of light, carrying the ship along with it, instead of the ship itself moving. So that's an interesting idea. It's a lot more similar to Star Trek, if you like Star Trek. It's a lot more similar to warp drives in Star Trek than hyperspace travel, I would say, but it's still one of the bigger contenders for faster than light travel. One of the other more esoteric methods is traveling via different dimensions. In particle physics, one of the more strange theories that are intended to wed quantum mechanics, our best scientific theory of very small things, and general relativity, our best theory of gravity and very big things, turning them into one theory is called string theory. In string theory, all elementary particles are described by little vibrating strings that vibrate at different rates. And one of the common requirements of string theory is additional dimensions beyond the 3 space and 1 time that we know, sometimes up to 7 more dimensions for 11 total. These dimensions are thought to be small and scrunched up, but perhaps if you could unscrunch them with some probably negative energy again, because it's basically magic, if you unscrunch them, perhaps you could get a ship through these other dimensions, bypassing a lot of the restrictions we have in our own and crossing our 3 dimensions much quicker, in much the same way that you can move your hand across a piece of paper much more quickly than you can run all the way to Chicago or something. So those are some of the possible hyperspace methods. And of course, one of the Star Wars characters who's excellent at going through hyperspace is Han Solo. And one of the things he claims he can do is run the Kessel Run in less than 12 parsecs. Now, a parsec is, of course, not a measure of time. It's a measure of distance. A parsec is about 3 1/3 light years. It's what astronomers use to measure longer distances than light years. So one of the explanations in Star Wars for Han Solo's comment to Obi-Wan Kenobi is that he found a better passage through the Kessel Run that cut down the travel distance and therefore the travel time, primarily the travel distance. So on the left here is the reason in Star Wars why the Kessel Run is so deadly. The Maw, a cluster of black holes, which are absorbing matter that is orbiting around them. Now, to form a cluster of black holes, for a start, they probably all need to be around stellar mass. And by stellar mass, I mean somewhere in the 5 to 10 times to 20 times the mass of our sun range, because any larger than that, and they would tend to coalesce into a single black hole. To form this many black holes in close proximity, you would probably need them to all begin in a globular cluster, which is a type of star cluster where all the stars are quite close together and form something roughly resembling a sphere. There are a number of globular clusters in our galaxy, some of which you can observe with the naked eye. And there are some examples in the Messier catalog, which is a classic catalog of generally naked eye objects. So if you can go out and see a little round smudge in the sky at night or through binoculars, you may well be looking at a globular cluster. Check your star chart. Well, how could you speed up the Kessel Run when you're going through a load of black holes? Well, you could use their gravity. Black holes themselves are singularities. In general relativity, they arise from the equations because they suggest that you can have a point of infinite density. This point of infinite density has such high gravity, such a bending of space-time that not even light itself can escape. So with gravity that high, you can do something called a slingshot, where you accelerate in on a parabolic or hyperbolic trajectory, which are 2 different curves that allow you to enter then exit an orbit. And you can blast through and be accelerated out the other end by the high gravity. Now, this isn't something I've just made up. Gravity slingshots are orbital mechanics that are used in our own solar system by many, many probes. Voyager 1 and 2 and Cassini, they all used, and our probes to Mars, they all use gravity slingshots to get them quickly where they need to go without expending huge amounts of fuel, having to pack lots of fuel on board the spacecraft. So it's actually a very efficient way of speeding up space travel. There's an actual creature living near a black hole, near the black hole in the Maw in Solo, a Star Wars story. However, I can't really comment on creatures living near black holes because I am an astronomer, not a biologist. However, all of the material whirling around the black hole is reasonably accurate. On the right here, I'm actually showing, this is an image of a black hole, or not a black hole itself, but the material around it. So this was taken by the Einstein telescope team very recently, last year. I recommend looking up black hole images, and this should come up. To learn more about the story, it was a huge undertaking, a huge team, lots of students, graduate students, undergraduates working together to get this image. And what we're seeing here is the bright light that's emanating from the material that's orbiting this black hole. It's not being sucked in, it's orbiting and then slowly falling in much the same way that spacecraft burn up in the Earth's atmosphere, as recently happened to a Chinese booster rocket, which landed in the Indian Ocean. So what essentially is happening here is this orbiting material is rubbing against itself, creating huge amounts of friction, heating it to extremely high temperatures, and putting out things like X-rays and gamma rays. If you want to learn more about black holes, I strongly recommend you come back for Dr. Abby Stevens' talk in a couple of weeks, where she's going to be talking all about her research into black holes. I personally don't research black holes. I tend to research what comes just before them, supernovae and massive stars. So black holes themselves are very intriguing objects, and I recommend looking into them a little more if you're interested by them. So with that, coming to the end of my talk now, if you're interested in the science behind Star Wars, there's a few resources I strongly recommend you look into. First, if you're interested more in the mathematical side, the astrophysics side, the Star Wars Technical Commentaries by Curtis Saxton, who's an astrophysicist, is quite an old website now, but still has excellent information where he goes through frames of the movies painstakingly to determine things like how much energy the Death Star needs, how fast a Star Destroyer is traveling, what is hyperspace, all the questions that I'm touching on in this talk. He goes into huge amounts of detail. So I recommend looking that up if you're interested about more detail, especially mathematical detail, about the scale of the Star Wars universe and what it might mean. If you want something a little more down to earth, the wonderful Skype a Scientist service recently did a Science of Star Wars talk on May the 4th, and Dr. Abby Stevens was part of that as well, talking about the astronomical side, but they also had a biologist and an astrobiologist on talking more about the aliens and planets of Star Wars, which you might find interesting. And of course, I am forever indebted to the NASA website, which has huge amounts of information for modern space missions and old space missions, where you can learn interesting things about the moons of Saturn or transiting exoplanets. So with that, I hope that was interesting, and I'm very happy to take any of your questions.
Thank you very much, Andrew. That was certainly interesting for me as well, to learn a lot more about how Star Wars links to things either better or worse from what we know in science. So we have a number of questions. I will say as well, please feel free to keep on asking questions on Facebook and Twitter, and I will get to them at the end. We've already got a number. Some I think might be easier for you to answer than others, but we'll see. So actually the first two that came in were asking about planets. I think they're planets that are in Star Wars. So apparently Darth Vader is from a planet called Mustafar, I think. I'm not sure.
Yes, he has a castle on Mustafar, yes.
And apparently it's like a volcano planet. So the question is, would that really be a habitable planet? Would you be able to build a fortress there?
Well, that's an interesting question. So Mustafar to me strikes me as something of a primordial planet. This is a planet that's in the early stages of formation. It's still extremely hot. All of the material is being smashed into each other to create the planet relatively recently. And by recently, I mean astronomical timescales. So, maybe a few tens of millions of years have passed. But yes, that kind of strong volcanic activity would make it very difficult to survive on. I think the kinds of gases that volcanoes put out are generally not the kind that humans want to breathe. So I would say you would definitely need a suit like Darth Vader to really be able to survive on Mustafar. But yeah, I mean, planets like Mustafar would definitely exist. Surviving on them is another matter. I believe, though don't quote me on this, that there was a period in the Earth's history when it was primordial, when there was actually a large amount of oxygen in the atmosphere because of volcanic activity. However, the temperatures and the actual pressure of the atmosphere were probably not very habitable. So I would say definitely you need to be Darth Vader to live on Mustafar.
So his suit was multi-purpose in the end. Very
yes.
Nice. Okay, and another similar kind of question, this one from Evan on Twitter, asks, Luke Skywalker's planet, Tatooine, had 2 stars. Is that possible to have 2 stars? I'm paraphrasing it. Is it possible to have 2 stars so close to a planet?
Well, I mean, as I showed with the TOI 1338b, yes, planets like that do exist. Now, how close they are to the planet is another matter. Once the problem with a system like that is that if the planet is quite close to the two stars, you end up with very complicated gravitational interactions. Essentially, with TOI 1338b, the planet is far enough away that from the planet's point of view, the two stars almost look like one gravitational object. It orbits the center of mass of those two stars. But if you start to get very close, if the stars are different masses in particular, they will start to disturb the planet's orbit. And it is unlikely that a close-in planet would be in any kind of stable orbit around a binary star. You would expect it to be ejected quite rapidly. And in fact, the so-called three-body problem is one of the most complex problems in gravitational physics. It takes supercomputers thousands of hours to simulate what you might think of as relatively simple things of, two stars and a planet. And quite often, like most of the time, you'll end up with a chaotic system where the planet is just kicked out into space, and then the stars go back to orbiting each other.
Interesting. Yeah. So actually a question that's just come in from Mary kind of leads on from that. It's kind of out of order, but it leads on. Says, do you think there are many other planets that exist around or orbit two or more stars? So I guess out of all of the exoplanets that we've found, are they all around single star systems, or are there a fraction that are around two stars?
Yeah, the vast majority of exoplanets we've discovered are around single stars. That's mostly because of the methods we're using to discover them. As I said, it's very difficult to distinguish a planet eclipse from a simple stellar eclipse. If two stars are eclipsing each other, it's very difficult to pick a planet out, which is why we had a high schooler doing an internship looking through the data by hand, by eye, to determine if they could find a planet there. Usually when we look for planets using exoplanet surveys, there are computer systems that we use, computer programs that will pick out the eclipses and say, look, there's a planet here, and then astronomers will go and look at them more closely. But that's almost impossible to do with a binary system. So the vast majority of planets have been discovered around single stars. However, from my point of view, I personally studied binary stars a great deal, and the vast majority of stars are actually they are formed in multi-star systems. Therefore, it is reasonable to expect, just based on pure number statistics, it is reasonable to expect that a large proportion of planets may be found around binary systems. Will they be in stable orbits? Will they be easily detectable? I don't know. But I think it's very reasonable to expect a large number of planets around multi-star systems.
So what you're saying is we need an army of high school students to look at all of the data.
Exactly.
If any
I wouldn't, so
get in touch.
Yes, precisely.
Okay, excellent. Thank you. So Susan asked, do you think there could be life in our solar system, i.e. Europa? I think you mentioned water on Europa.
So I think Europa is personally, it's always piqued my interest as one of the planets, well, not planets, but one of the locations in our solar system where life is probably the most likely. It's something, since I saw documentaries and learned that Europa had potentially a water ocean, it's been very exciting, and I'm really looking forward to that Europa Clipper mission. There's also been missions proposed to send probes to drill through the surface of Europa and try and send a submersible, potentially, if we can prove there's a water ocean there. So I think Europa is one of the very good candidates. The recent discovery of phosphine, potential discovery of phosphine on Venus, is another indication there may be some kind of bacterial life on Venus, which would be extremely exciting, since Venus is is very similar to Earth, just much hotter. It's essentially Earth that has undergone runaway greenhouse effect. So I think those two are the most likely candidates. Obviously, Mars is always comes to the forefront of people's minds, and we have two wonderful rovers on Mars right now. I recommend you check out the little flights of the helicopter Ingenuity. Those are really great to watch. But Mars is so dry. I think it would be, if there's life on Mars, it would have to be very deep under the surface in whatever water deposits are there, at least any life like we have on Earth. I can't comment on anything beyond that, as I'm not a biologist. So anything beyond what we have on, what we kind of know of on Earth, I'm completely out of my wheelhouse. But I think Europa and Venus are top of my personal list anyway.
Okay, very cool. Yeah, I saw the thing about phosphine, and I never knew. I don't know if you know. I don't know if we know, is it liquid water, or do they know that it's liquid underneath the surface of Europa, but they don't know?
It's presumed based on the mass of Europa. You can calculate roughly the density, because we know the size of it, of course. So mass divided by volume, you get density. So the density of Europa suggests that it is mostly water.
Okay, very cool.
And a lot of the other moons of Jupiter are also very icy. So it's a good chance it's mostly water ice.
Yeah, very interesting. I guess I can skip around in the questions as well, because there was another one, if I can find it, about life. Oh, you were talking about the different methods for planet discovery, and Eric asked, can any of those methods also be used to discover life?
I would say I think the only method that you could reasonably use to look for life could potentially be the transiting method. Because with the transiting method, you can also get spectra. So I mentioned spectra earlier. That's when we look at light at multiple wavelengths. And when you look at light at multiple wavelengths, you can determine what elements are in the atmosphere of something. So when a planet is transiting, if we do transit spectroscopy, and we see the atmosphere of the planet by essentially looking at the light reflected of it from its star, we look at that atmosphere, we can look for the signatures of certain atoms and molecules that may indicate, much like phosphine, that may indicate there's life on the planet. The other more exciting, sorry, carry on.
Sorry, does that mean that they're not natural? We wouldn't expect them to be natural?
Right, yes. So there are these specific fingerprint molecules that astrobiologists have been trying to come up with that only life could produce, that you couldn't produce in a reasonable amount, a detectable amount using other methods. So phosphine is one that's generally paraded as one of the clear signs. And obviously, a large proportion of oxygen compared to other gases might be indicative of some kind of photosynthetic process. The other interesting thing that related to science fiction is the idea of, well, potentially not science fiction, is the idea of mega constructions. If you have some kind of giant space station, or what's called a Dyson sphere, which is where you put giant panels around a star to take all of its energy, those kinds of constructions could potentially be detected with transit photometry. And in fact, there was a very exciting discovery a couple of years ago now, where they thought they may have detected such a megastructure, but it turned out the most likely explanation, as it usually is, was a trail of comets, which still is very exciting scientifically to see comets in another system. But the initial reaction was, could this be some kind of megastructure trailing behind a planet? And that would have been exciting, but unfortunately unlikely, but still the chance is out there. So that's what I would say in terms of these particular, the methods I talked about.
At least if we thought of it, then we might be out looking for it and have a chance.
Exactly.
So that actually leads back to one of your previous points, into Shika's question, who said that they were always curious about how much power it took to keep the Death Star operational day by day. And I think you gave the example of the output of the sun.
Yes.
Asked if it could be related to something like the amount of energy the USA uses in a day, or anything.
Oh goodness.
Maybe this will be one that we can come back and respond to later on Facebook if there's.
Yes, no, I'd happily do the calculation and follow up on that. Yes, but definitely, I'm happy to do that. That's I just don't know the the wattage of the US.
More than the power output from the sun. Is that per second? I guess. Like.
Yeah. So when it's firing at super laser. Again, I urge you, if you want some hard numbers, I urge you to look at Curtis Saxton's technical commentaries. He has a lot of really fun numbers. But yeah, 5 times the output of the sun. The sun puts out about 10 to the power of 32 watts, which is a lot of energy, and it's a lot of power.
And already then, if that's in a second, then you can work out divide that by how many seconds in a day, and then we just
and the power consumption of the US is probably something like in the terawatts level, I assume, which is 10 to the 12 watts.
That's still like thousands of years, basically.
Yeah, so you're looking at 10 to the 20 watts of 10 to the 20 of the United States on the back of the envelope. But I can definitely get you a more accurate number afterwards.
Okay, great. Thank you for the question. And I've got one more for now, which is from Koji. I think this was related to the Chinese rocket that you said crashed in.
Yes.
It crashed in the Indian Ocean, and Koji asked, how did they know that it was going to crash in the Indian Ocean and not in a populated area?
Well, this was a bit of a mistake by the Chinese Space Agency. They launched their rocket, and one of the boosters fell off at the wrong point, and so it started deorbiting, which is just a term for saying that it started burning up in the Earth's atmosphere and started slowing down much more rapidly and in the wrong time than anticipated. So it was slowing down, friction was burning the Earth's atmosphere, and we have a lot of tracking stations on Earth that track these kinds of objects. So people were using radar and satellites to track the course of the object based on its last known positions. And the US Space Force, for example, was tracking it quite closely. And essentially what you do, you do a lot of mathematics, and you calculate how big the booster is, and you know roughly what the density of the Earth's atmosphere is at the altitude of the booster, and you can use that to calculate how much it's going to slow down. And when it starts to really slow down, where might it be in its orbit? And it turned out that ended up landing in the Indian Ocean. It was actually seen, I believe, streaking across Africa on one of its last passes around the Earth. Wow. And I think it was spotted maybe in Saudi Arabia as well. There are a few videos out there of it shooting along. One of the people to look up, I think, was it Jonathan McDowell, I think? He's one of the guys at NASA's Jet Propulsion Laboratory, I believe, if I remember correctly, or is it Harvard Center for Astrophysics? But anyway, if you look it up, there's a lot of really good news articles out about that, and I can find a couple for Dan to put in the Facebook chat afterwards.
Sounds good. Yeah, I mean, I can see why people ask, because I'm continually fascinated by how accurate people can be with those predictions. But if you think about it, we also send spacecraft to other planets like Mars.
Yes.
Manage to land objects within a mile radius probably of where they're meant to be on Mars. So
I will say, in the case of this particular booster rocket, there was some concern in the space community, in the kind of space technology community, because it was quite difficult to track. They really only had information for it when it was quite high in the atmosphere, and everything after that was heading towards just being calculations rather than actual radar or detection. So that one was a little edge of the seat for a while.
Okay, well, I think that's all we have time for, but thank you so much, Dr. Fullard, for coming along. That was fascinating and lots of discussion. So thank you.
No problem. I hope everyone enjoyed it.
And yeah, we'll look forward to seeing you again soon. So thank you very much also everyone else for joining. And you can find us on Facebook and Twitter at GLL_MSU on Twitter and GLL MSU on Facebook. And be sure, as Andrew let you know, the next talk in our roster, the last for the summer, will be Dr. Abby Stevens. So please join us again in 2 weeks' time. So,
I strongly recommend it. Abby's a great speaker.
So thank you very much again, everyone, for joining. And I hope you have a good rest of your week and a good weekend ahead. Bye-bye.